Okay, so last class we spoke about the group structure of the Möbius transformations of P1C and the group structure of Möbius transformations of C bar. What we saw was that the fact that the Möbius transformations of C bar form a group can be easily reduced to the fact that the Möbius transformations of P1C form a group. And that this form a group we had already proved very easily, right? So somehow in the end we showed that the Möbius transformations of P1 form a group and the Möbius transformations of C bar form a group without doing many tedious computations, as is common in many textbooks, for instance. Okay, I would say we did it rather conceptually. Then we showed that the action of the group of Möbius transformations of C bar on the set of triples of distinct points of C bar is simply transitive, right? So that if you give me two triples, each one of 3 different points of C bar, then there exists exactly one Möbius transformation that takes this triple to the other in order, right? The first one to the first one, the second one to the second one, the third one to the third one. Transitive because for any two given triples there is a Möbius transformation that does the job. Simply transitive because there is exactly one Möbius transformation that does the job of taking this triple to this triple. Okay. Afterwards, we show that any Möbius transformation takes circles in C bar to circles in C bar, and hence disks in C bar to disks in C bar. And we finished the class by saying how one decides if you give me the two triples, how to decide by just looking at the triples which of the two disks determined by this triple goes to which of the two disks determined by this triple, right? I mean, this triple determines a circle, hence two disks, and likewise with this triple. And then take one of these disks. The image I know is one of these two. And what we did was we explicitly decided which one by just looking at how the two triples are combinatorially configured. Okay, now today I'm going to show that the fixed points of any Möbius transformation can be computed explicitly, right? So because once we know this simple transitivity on triples, then we know that if you give me a Möbius transformation and this Möbius transformation has 3 fixed points, then it has to be the identity on the whole of C bar, right? So the only Möbius transformation with more than 2 fixed points is the identity, right? In other words, any Möbius transformation different from the identity has at most 2 fixed points, right? So today I'm going to see that this at most 2 fixed points can always be computed explicitly in terms of the entries of any matrix representing the transformation. And second, I'm going to use the fact that there are always at most 2 fixed points to obtain a classification up to conjugation, and to see that every Möbius transformation is conjugate to one of the standard examples. Now notice that this simple transitivity then plays an essential role, right? This simple transitivity implies that there are at most 2 fixed points, and the fact that there are at most 2 fixed points allows us the classification, right? So this simple transitivity really plays an essential role in the whole theory. Now, before going into the section, let me say a few more words about this simple transitivity. Because, of course, now we know that if you give me two triples of distinct points, there is exactly one Möbius transformation sending one triple to the other in order. We know that now, right? But how do you come up with that? How do you know that it has to be 3? right? Where does the 3 come from, right? Um, for instance, I mean, now knowing that, the simple transitivity on triples, now we know that if you give me 2 quadruples of distinct points, it may be the case that there does not exist any Mobius transformation taking one to the other. Okay. On the other hand, if you give me two pairs, two ordered pairs of distinct points in C bar, well, I know that there is at least one Mobius transformation sending this one to this one and this one to this one, but actually there are many, right? So in the case of pairs, you don't have the action is not simple. I mean, you have transitivity, but the action is not simply transitive. And in the case of quadruples, the action is not even transitive, right? So how do you know that it has to be 3? You know, it has to be triples. And the point is that this simple transitivity can be seen, can be interpreted as the shadow on a P1 of linear algebra, right? It can be seen a shadow on P1C of a linear algebraic fact, namely the following. So in the basic courses of linear algebra, we are all taught that if you gave me an ordered basis of a vector space, then to define linear transformations from that vector space to any other vector space, it suffices to decide where you want the vectors in the basis to land, right? In other words, one proves that if for each vector in the ordered basis we choose what images we want them to have, then there exists exactly one linear extension of that rule to the whole space. So it is possible to extend any function from the basis to the space. It is possible to extend it linearly in a unique way to a linear function defined on the whole space. Right? So why do I say that that simple transitivity is a shadow of this? Well, let us analyze to simplify for simplicity under the assumption that this one is the standard basis of C squared. So here it is. So this one is V1, which is the vector 1, 0, and this one is V2, which is the vector 0, 1. And then, first of all, notice that if we use this ordered basis, V1, V2, to give this bijection between P1C and C bar, it turns out that the vector space, the vector subspace spanned by V1 corresponds to infinity, and then if I take any vector subspace different from the horizontal one, then one looks at how it intersects the horizontal line at height 1, and then looks at you know, at the x coordinate, and that's the complex number it corresponds to, right? So okay, so this was a brief reminder of how this bijection works. Okay, so suppose we fix this basis, right? And then here, of course, you can see the vector, the sum of these two vectors, which is the vector 1, 1, which corresponds to the element 1 of C bar, right? Under this bijection of between P1C and C bar. Okay, now a linear map, I mean, by definition, a Mobius transformation of P1C is the shadow of a bijective linear map, right? And the theorem says that a bijective linear map is determined by deciding where these two go. So I imagine that I decide that, you know, that V1 goes to this vector, That's the behavior I want of the linear map, and that V2 goes to this vector, so that's the behavior I want of the linear map. Then, of course, then everything is decided, right? Because then what I'm saying is that I want this element, which is the 0 of C bar. I want it to go here. I mean, the linear maps, not the linear map, the Mobius transformation induced by this linear map sends 0 to this one and sends infinity to this point. And then because this point is the sum of these two, then the Mobius transformation has to send this one to this one, right? Okay, and then you say, okay, but so what do you mean? I mean, then why the 3? Where does the 3 come from, right? I mean, you said that everything was decided once you decided that this is the image of V1 and this is the image of V2, because then their sum has to go here, and so this point has to go to this point under the Mobius transformation. Sure, but notice that here, you know, here it is not let's say here it is not quite essential that it is this vector where I want to send V1 in order for this point of C bar to be sent here, right? In other words, I can choose any other non-zero point on this vector subspace. Let's say I can choose, let's say, this other vector, and I can say, okay, now I want a V1 to go there. Yeah, okay, and then, but at the level of linear of Mobius transformations, I would still have this point going to this point. And similarly with this other direction, it is not essential that it be this vector the image of V2, right? Because I can say, no, I mean, take this other vector, multiple of the original one, and send V2 there. Right, then the Mobius transformation in the end would send again 0 to this point, right? Okay, so this means that we have freedom in rescaling here without affecting the fact that we are sending 0 to this point and infinity to this other point, right? So we can rescale the images. We have freedom to rescale the images of V1 and V2. We have freedom to move them without changing the images of this and this, right? Which would be then this and this, right? Okay. Now notice that if we rescale both by the same scalar, then the linear transformation changes, but the Mobius transformation doesn't at all, right? So we can say, okay, then to really see the simple transitivity, let's say that this one I fix and I decide to rescale only one, right? I need to rescale only one, right? Because if I rescale both by the same scalar, the Mobius transformation doesn't change. So this tells me you can forget about rescaling one of them, just rescale the other one. Okay, and then notice that then if I for instance, if I rescale this one, then the law of the parallelogram tells me, okay, now the sum arrives here, so I actually moved the image of one, I moved it a little bit, right? So that's the point, that the freedom in choosing the image of the third one comes from, you know, the freedom to rescale, and that is why it's 3, right? It's 2 for the basis plus 1 that you have a 1 freedom to rescale. So let me show you this on a small program that I wrote. So there you can see the x-axis, the y-axis, and the line at height 1. And then let's say that I'm still working. So let me move this here. Right. So let me see. I mean, I'm still working with the same basis in the domain, right? Right. And with that same basis is that I'm obtaining the bijection sketched here between C bar and P1C. it's sketched in the fact that I'm drawing here this horizontal line at height 1. Okay. So let's say that I want the image of V1 to be this one. So you can see the red dot. So that's the image of V1 under the linear map. Under the linear map. So this means that I want the image of V1 to be this point of intersection, right, at the level of Mobius transformations. Okay, let's say that I want the image of V2 to be that one, this one that I click here, right? This one. So this means that the image of this point of C bar is not this point, but it's crossing with it is crossing. Okay, given those two choices, right? V1 going here and V2 going here, you see the point 1 is forced to go here, right? Okay. So which means that the point 1 of C bar is forced to go here. Okay, but now let's say just rescale here, and you see when we rescale, of course the image of the point 1 of the image of 1 1 under the linear map moves, and with it moves the image of the point 1 of C bar under the Mobius transformation, right? So somehow at the level, the Mobius transformation somehow forgets about what's going on here and only sees this shadow of these crossings, right? So let's see, let's move, right? And that you see, and then there you go, there you have your simple transitivity, right? If you want 1 to go to this point, then you just move, you just rescale enough. Well, okay, so I mean here it's going to be a bit not so easy. There you go. Okay. So simple transitivity is the shadow of this linear algebraic fact. Okay. Oops, sorry. I have to appear myself again. Here, there you go. So let us start then speaking about the fixed points. By the way, this page here is now available in the website, right? So because this I didn't cover in the class yesterday, but now you can find this one in the lecture notes of not yesterday, last class. Right? Okay, now let's speak about fixed points, right? So, so as I said a moment ago, the fact that given any two triples of distinct points, there is exactly one Mobius transformation taking one triple to the other in order, automatically tells me if a Mobius transformation has 3 fixed points, then it has to be the identity, right? Because the identity fixes each of those 3 points, and the identity is a Mobius transformation. So if any Mobius transformation does the job, then it has to be the identity, right? So every Mobius transformation has at most 2 fixed points. Okay, yeah. The proof we gave was I would say very elegant, but we still have 2 questions. Okay, at most 2 points, but is there any Mobius transformation without fixed points? How many? Right? And then do there exist Mobius transformations with exactly 1 point? And do there exist Mobius transformations with exactly 2 points? Well, that's one thing, right? And second, okay, we know that any Mobius transformation different from the identity has at most 2 points. Okay, how do you compute them? Explicitly, and by explicitly I mean in term, to give like a general algorithm or procedure that given any matrix gives as an output the fixed points of the Mobius transformation. Right? So these 2 questions we are going to answer, and actually we are going to answer the second question, and in answering it, we are automatically going to answer the first one. So I mean, do there exist Mobius transformations with exactly one fixed point? Yes, because translations only have infinity as a fixed point, right? Any translation fixes only infinity, but okay. And then do there exist with 2 points? Yes. You know, for alpha different from 1 and 0, multiplication by alpha has only 0 and infinity as fixed points. Okay, so do there exist Mobius transformations with 0 fixed points? These we're going to answer. But okay, but let's start. Take a 2 by 2 a matrix for which you know that the Mobius transformation is not the identity, right? So the matrix is not a multiple of the identity matrix. Okay, and then notice if gamma is 0, then this one fixes infinity, right? And then infinity is kind of a special point from the arithmetic point of view. I mean, arithmetical point of view. So we are going to divide our analysis on you know on whether infinity is a fixed point or not. That is in terms of whether gamma is 0 or not, right? Which this is what I can see directly in the matrix, right? Okay, so I analyzed 2 cases. The first one. So here, let me move. Yeah. The first one, suppose gamma is 0. So this entry is 0. So first of all, I mean, we already noticed infinity is a fixed point, and it remains to see whether there's one more or not, right? Okay, so fixed points, you know, are the points that satisfy mu a of z equal to z, right? So it's obvious that finding any other points, namely the points that are complex numbers and are fixed by mu of a, amounts to just solving this equation, right? This is mu a of z, and this, and now for complex number z, because for infinity it's solved in here. Okay, and now here what happens? Well, that if this is 1, when this is 1, we cancel, right? And then we obtain no solution, right? Because beta is what? Right, because if this is 1, that is because alpha is equal to delta, and then beta cannot be 0, because if it were 0, then we would have that a is a multiple of the identity, right? Okay, so if this is 1, then this cancels with z, and then there is no solution, right? Because beta is not 0. Okay, and if it's not 1, then you know then we just solve for z and see that this one is a root of the equation, and then hence it's a fixed point, right? So in the case when gamma is 0, that is when we have when our matrix has this form. One has 2 possibilities: either exactly one fixed point, namely infinity, when that quotient alpha divided by delta is 1, right? So when alpha and delta are equal, and exactly 2 fixed points if they are not equal, in which case you know you find that the fixed point is this one explicitly in terms of the entries of the matrix. For one thing, and second, it's just by solving this equation for z, and you know, super easy to solve equation. Okay, so this solves the problem when gamma is 0, and then we see that there's in that case there's at least one fixed point, right? So infinity and possibly someone else, if gamma is 0. Okay, now next case, suppose it's not 0. Then, well, first of all, infinity is not a fixed point, so in looking for fixed points, I can forget about infinity, not worry about infinity whatsoever, and worry about the problem of fixed points only, about only finite fixed points. I mean only points in C. Okay. Now, again, for when except maybe well, okay, notice that if the denominator is 0, right? Namely, when is the denominator 0? Well, since I'm assuming that gamma is not 0, the denominator is 0 in this point, which is a finite point, but then the value at that point of this expression is infinity. So this guy is not a fixed point. I can worry about solving this equation without having to worry about the point where the denominator is 0 as a potential fixed point, right? Okay, right. But then doing this, this I can pass this multiplying to the right and so on. So I realized that it really comes down to solving high school quadratic equation, right? So explicitly using the quadratic formula, in Mexico usually referred to as la chicharronera. So using la chicharronera, we can find the roots of that polynomial, which are these ones. Right? And here, of course, notice, this could be 0 as well. I'm not saying that it is not, right? Okay. Anyway, so when gamma is 0, one has, well, since since we have seen that when gamma is 0, the fixed points have to be roots of this one, and vice versa. Then one has exactly one fixed point if this formula throws only one number, namely when the interior is, when the part inside here is 0, inside the radical, right? And then of course the fixed point then is this, right? Or exactly two fixed points, namely when one takes plus here or minus, right? In both cases, we notice that the fixed points, namely the roots of this polynomial, are expressed explicitly in terms of the entries of the matrix A with which we decided to represent our Möbius transformation, right? Okay, and here again, we have at least one fixed point always. Right? So now we see that every Möbius transformation has at least one fixed point, and we have some sort of algorithm to find them explicitly, right? Like in the first step, one asks whether gamma is 0 or not. If it's 0, one applies something. If it's not 0, one applies some other thing, right? And everything comes down to solving an equation of degree at most 2. So, okay. Okay, now, let me denote by, the set of fixed points of a transformation to be, fixed, in C bar, right? So the fixed points in C bar of this transformation. Right? I mean, more generally, if I have a, if I have the action, if a group is acting on a set, and I take an element of the group, then I can say, okay, fix of that element in the set where I'm saying the set is X, and then I define it to be the set of fixed points of that G in the set, right? So here it may look like a mouthful, but later on we are going to change, and instead of considering C bar, we are going to consider different things like the upper half plane or the Poincare disk and so on. Okay. Now we know that every Möbius transformation which is not the identity has either exactly one fixed point or exactly two fixed points, right? We already saw some examples, namely translations, which have each of which has exactly one fixed point, and multiplication by a non-zero, non-one complex number, right? Alpha different from 1 and 0, in which case 0 and infinity are fixed points, so two different fixed points. And for those ones, we could achieve some basic geometric analysis because they were very simple functions. Okay, now what I'm going to do next is, if you give me a Möbius transformation which is not the identity, I'm going to look at its fixed points and use its fixed points to conjugate to a Möbius transformation that if my Möbius transformation has only one fixed point, I'm going to use its fixed point to conjugate it and obtain a Möbius transformation that fixes infinity as a conjugate. And if my Möbius transformation has two fixed points, I'm going to use those two fixed points to conjugate and obtain a Möbius transformation that fixes 0 and fixes infinity, conjugate to the original, right? So it would be useful to know that the results, that knowing that the result has only one fixed point and it's infinity, then whether that implies that it's a translation, and having two fixed points and those points being 0 and infinity, to see whether that implies that it's multiplication by some alpha. Right? And that's what this lemma says. So if you give me a Möbius transformation for which you already know, so somehow after having conjugated, let's say in the process I have in mind, it has infinity as its only fixed point, then nu is a translation. And similarly, if you have a Möbius transformation and somehow you already know, let's say after conjugating, which is after doing what I have in mind, you see that the fixed points are precisely 0 and infinity, then nu is multiplication by a non-zero complex number alpha. And this is a lemma. It's very easy to prove. It's very, very easy to prove, and I leave it as an exercise. Okay. Right. I mean, you have to play with the entries of the matrix and with the definition. You know, with the famous formula alpha z plus beta divided by gamma z plus delta, and so on. Right. So it's quite easy. Now, next thing, we introduced already these sets. I mean, this notation for the set of fixed points of any given transformation. So in general, I wanted to show that if you give me two bijective functions, then you can, you know, if you let's say that you have two bijective functions, and that for some reason you know the set of fixed points of f, and then want to compute the set of fixed points of its conjugate by g, and the result is quite nice. In order to know the set of fixed points you want to know, you only have to take the fixed points you knew already and apply g to them, and that gives you precisely those fixed points of this one. So in other words, the fixed points of the conjugate are the fixed points of the conjugate by g are g of the old fixed points. Okay, and now the theorem that allows us that will allow us later on to perform to extend the geometric analysis we did for the standard examples to the general case of arbitrary Möbius transformations. And the theorem is that any Möbius transformation is different from the identity, is conjugate to one of the standard examples. And as I said, the trick is to knowing that the number of fixed points is exactly 1 or exactly 2, perform a trick to conjugate and obtain something that either fixes only infinity or fixes 0 and infinity, and then, well, this lemma does the job. Okay. Okay, so that's what we do. So in the first case, suppose it has only one fixed point. Let's say the fixed point is z0 or z0. Okay. Now, if this fixed point is already the point at infinity, there's nothing to do, because there's nothing left to do, because then nu itself is a translation and it's conjugate to itself. Okay. Okay. So suppose it's not infinity. All right, and then one says, okay, so because we know this lemma somehow, and because we know that that the fixed points of the conjugate are G of my original fixed points. I want some Mobius transformation G that takes Z0 to infinity. Okay, but once you tell me that, we are done, because what we are saying is I want Z minus Z, I want Z minus Z0 to appear in the denominator. And then in the numerator, let's say 0Z plus 1, let's say. So I only need, so this expression, 1 divided by Z minus Z0 gives me a Mobius transformation, and sends Z0 to infinity, which is what I needed. Okay, so this is what we do. And then this conjugation is a translation. Okay, so fair enough. And then now you can imagine what's the other, the trick for the case where you have two fixed points, right? I mean, when you have two fixed points, then again, I mean, then either infinity is a fixed point or not. If it is a fixed point, you know, the other point has to be a complex number. And then, well, you already have infinity as a fixed point. Then you only have to worry about forcing the other point to become zero. So because of this lemma, and because you know that the fixed points of the conjugate are G of the fixed points of the original fixed points, you know that what you need is a Mobius transformation that simply sends Z0 to 0, right? And well, infinity to infinity, right? But that again is quite easy. I mean, because this expression sends infinity to infinity and vanishes at Z0. So we are done, right? Because it is a Mobius transformation, right? So in that case, the lemma follows, and then finally, when infinity is not a fixed point, then both points are complex numbers, and then this exercise, and again this lemma tell you that what you want is a Mobius transformation that sends one of them to 0 and one of them to infinity. So let's say that I want to send Z0 to 0 and Z1 to infinity. Then, okay, then I want this in the numerator, and then I want this in the denominator, and then I only need to check that this is a Mobius transformation, so realize it by a matrix. Then that's what I do. Notice, if this is because I decided to send this one to 0 and this one to infinity. I could have as well decided to send this one to infinity and this one to 0, in which case I would have to take the fraction I wrote, this fraction, but not like I wrote it, but it's reciprocal, so it's inverse. Okay, but in any case, the important thing is that Mobius transformation sends the fixed points of this one to 0 and infinity, which become the fixed points of the conjugation. And we are done. But notice, it is important in this sub case to see that you could have chosen this one or this one, right? So it is not the case that there's only one Mobius transformation that does that conjugates this one to obtain the desired Mobius transformation. There could be many, right? Okay, so as you can see, the theorem in the end is fairly simple. It's fairly easy. You only need to, once you know this exercise and once you know this lemma, you know what you need. And once you know what you need, you write down what you need, and then you obtain your Mobius, your conjugating Mobius transformations that conjugate what you have into what you want. Okay. But having known from knowing that the number of fixed points was essential, right? So the simple transitivity was really essential. The simple transitivity on triples. Okay. So now we see that. Right. So now we see that every Mobius transformation, different from the identity, is conjugate to a standard example, right? And the next, and as I pointed out in the very last subcase, instead of sending z0 to 0 and z1 to infinity, I could have decided to send z0 to infinity and z1 to 0 and obtain another Mobius transformation that would have conjugated nu into the Mobius transformation multiplication by some complex number. But then this new complex number, how is it related to, the two complex numbers I could have obtained? How are they related? I mean, what I can see from that is that it is possible that multiplication by alpha and multiplication by alpha prime are both conjugate, right? And then, of course, I want to know when they are conjugate. And in general, I have my standard examples. Now I know that everything is conjugate to a standard example. Well, I want to be able to separate the standard examples, right? To know when two standard examples are conjugate and when not. So now, the first thing is conjugation preserves the number of fixed points, right? And it's again this beautiful formula. So in particular, if a Mobius transformation, Mobius transformation with exactly one fixed point is never conjugate to a Mobius transformation with exactly two fixed points to begin with, right? So, so in particular, for instance, translations are never conjugate to multiplications by complex numbers different from 0 and 1. Okay, so that's one nice thing to know. And another consequence is that we can focus on the two problems separately. Like first, classifying all the Mobius transform, deciding how many conjugacy classes are occupied by the translations, which are the standard examples that have exactly one fixed point. And then focus on the ones that have 0 and infinity as fixed points, right? Multiplication by some complex number. Okay. Okay. Now, how does one decide? I mean, there you can already see the statement, right? The statement of the proposition. And it's perhaps more important how do you know what to write in the proposition, right? So first, consider the case of translations, right? The case of translations, okay, and then you see, consider the possibility of translating along this vector, or the possibility of translating along this vector, right? So translation along this vector moves everything, right? Like this maps to this, and then, right? So, and the other one, of course, one has the kind of the corresponding picture, right? But you see, it looks to me something like this, like something like how to say, something like you can the first translation vector, somehow you can deform it through here, apply the translation, and then undeform, right? So in other words, it looks like if you give me two translations and you look at the translation vectors, that they should be conjugate, and they should be conjugate by something that simply multiplies by a non-zero complex number, right? That's what it looks like, right? By saying, okay, translating this way looks like first deforming into this vector, translating by that vector, and then undeforming. Okay, so noting that is that we try conjugation by something which is multiplication by a non-zero complex number. Right? And I do that, you know, like this analysis about deforming, translating, and undeforming, or undoing the deformation. You know, it saves me. You know, it makes my life easier by saying, okay, let me try to conjugate with with a matrix that has zeros here. That's the point. Okay, now next thing, you know, I remember that multiplying on the left with such a matrix what it does is it multiplies rows by the entries, right, by the diagonal entries. So this one gives me lambda and lambda beta 1. Okay, but then its inverse, which is, by the way, this one, is multiply now columns by the diagonal entries. So the lambda that was introduced here, this lambda gets destroyed by this lambda, or undone by this lambda. In any case, you can just do the direct computation and see that when you take this matrix representing the translation by beta by this, as I said, gives you this. And so it's enough if you set lambda to be beta beta prime divided by beta, and that way you see that these two are conjugate. And notice that in the end, the matrix that conjugates does precisely what I said. Okay. So somehow this kind of this informal or way too intuitive, you know, process of saying I deform, translate, and undeform or undo the deformation was actually correct. Okay. Then you know, from the fact that in the previous theorem here I noticed that I could have chosen to send z0 to infinity and z1 to 0 instead of z0 to 0 and z1 to infinity. And the fact that that would have worked in order to obtain that my nu is conjugate to a standard example, that tells me it must be the case that if you already have a multiplication by some alpha, that multiplication by alpha is conjugate to the one that has the same fixed points but does the opposite. So multiplication by one over alpha. And that's the case. And you see, what should be the conjugating? Well, just divide, you know, just 1 over z, right? Okay, which is represented by this matrix, this off diagonal matrix 0, 1, 1, 0. Okay, but once you see, the thing is, once you noticed the possible choice we had here, once you notice that is that it occurs to you that multiplying by alpha is conjugate to multiplying by 1 over alpha, and that the conjugation has to be the conjugating Mobius transformation has to be z goes to 1 over z. Okay, so you always have that you see, if you give me alpha and alpha prime, if these two sets are equal, because these two sets being equal is equivalent to saying that that alpha is equal to alpha prime or its inverse. If this happens, then they are conjugate. So the next step is, okay, is it the only way multiplications by complex numbers are conjugate? And the answer is yes. In other words, if you give me multiplication by alpha and multiplication by alpha prime, and they are conjugate, then it must be the case already analyzed. It must be the case that either alpha is equal to alpha prime, or alpha inverse has to be equal to alpha prime. So, okay, so assume that, right? Assume that. Then because again this beautiful identity, that the fixed points of the conjugation are G of the original fixed points. Because of that, when you conjugate, this one sends the fixed points of multiplication by alpha to the fixed points of multiplication by alpha prime, because we are assuming this. Right? Okay, so you have two cases. The easy case, when it sends 0 to 0, and hence infinity to infinity because it's bijective, and then you just play the game of knowing this and knowing that it sends infinity to infinity, what it means for the entries of the matrix, right? And then you see that the conjugation happens even at the level of matrices. And then you see that because you see, because this and this then tell you that this matrix has to be a non-zero multiple of the matrix alpha prime 0, 0, 1. So alpha has to be lambda alpha prime, and this one has to be equal to lambda times 1, this other one, the one that goes in the matrix of alpha prime. But then there you go. So then alpha is alpha prime. And something similar, and a similar analysis in the other case. A similar analysis in the other case, that where first this and the fact that mu of infinity would be 0 allow you to deduce that x and t are 0, so that these entries are 0. And then here is computation of how the conjugation by b then looks like explicitly. And again, the fact this tells you that then this matrix has to be equal to lambda times the matrix alpha prime 0, 0, 1, from which you deduce this, and this tells you that that alpha inverse is alpha prime. Okay, so we are done, and what we see is then what happens among the standard examples. All translations are conjugate in the Möbius group Möb plus of C bar. That's the first thing. And second, also among the standard examples, multiplication by alpha is conjugate by multiplication by alpha prime if and only if either alpha prime is equal to alpha or alpha prime is equal to alpha inverse, right? So it's kind of, in these other cases, the classification is like by pairs, right? And so you can see, so you see if you plot the value of alpha, which then covers then the whole complex plane minus 0 and minus 1. I mean, because we are interested in multiplication by alpha in such a way that we obtain a Mobius transformation different from the identity. Okay, and then for instance, this one and its inverse, they give you not the same Mobius transformation, but their Mobius transformations, they don't give you the same Mobius transformation, but those two Mobius transformations are conjugate. Or for instance, let's say that here I take the number 2, and here is 1/2, right? So both of them give you different Mobius transformations, but they are conjugate, right? And they are conjugate by exchanging 0 and infinity, which somehow tells you that up to changing 0 and infinity, up to exchanging them, multiplication by 2 looks and multiplication by 1/2 look alike, right? That somehow they have somehow the same behavior up to taking different charts. Okay, but so you see here I have the picture for all the possible values of alpha, right? I mean, alpha positive, different from 1, alpha in the circle, different from 1, and the rest, right? And what we see is, to summarize now, all Möbius transformations that have exactly one fixed point are conjugate. Okay, so if you give me two Möbius transformations, each one of which have the same fixed point, even if the fixed point is not the same, right? But if this one has exactly one fixed point and this other one has exactly one fixed point, then they are conjugate. Because each of them is conjugate to a translation, and all translations are conjugate, right? And any Möbius transformation with exactly two fixed points is conjugate to multiplication by alpha for some alpha which is almost completely determined by nu, because it's conjugate to this one, but also to multiplication by alpha inverse. Okay, so the point is, nu almost determines alpha, and actually what happens is that here somehow one really has to take this one minus 0 and minus 1, and then actually take the orbits of inverting, of kind of identifying alpha with alpha inverse. So if you really want kind of a set of representatives for those alphas, somehow you really, what's enough? I think it's enough to take, okay, for one you don't take it, right? So it's open, and then minus 1 you do take it, so here it's closed, and then you take, I think, the interior, this interior, of course, without taking 0, but you do not take this other semicircle. And I think this set that I just drew gives you a set of representatives, in the sense that now, if you give me a Möbius transformation with exactly two fixed points, then is conjugate to multiplication by alpha for some alpha that if you impose the restriction that it be here, then it's unique here, right? In that one that just went away. That set whose picture just went away. Okay. So let me finish the class then with a definition, right? Which is now that we have somehow the full picture up to conjugation, or of how the conjugacy classes in this group look like. Then I give names, right? So if you give me a Möbius transformation, if it has exactly one fixed point, I call it parabolic. If otherwise, so in the remaining case, which is when it has exactly two fixed points, well, it depends, and the definition is given in terms of this picture for alpha, right? If the Möbius transformation has two fixed points and is conjugate to, has exactly two fixed points and it's conjugate to multiplication by some positive real number, then I call it hyperbolic. So here, right? Here. If it is conjugate to multiplication by, if it has exactly two fixed points and it's conjugate to multiplication by an element of the circle, I call it elliptic. So if it's conjugate to a rotation, right? And finally, if it's not in those cases, then I call it loxodromic. So parabolic, if it has exactly one fixed point. Hyperbolic, if it's conjugate to a positive real homothenity. I mean, to a homothenity by a positive real number. Elliptic, if it's conjugate to a rotation, and loxodromic in the remaining cases. Okay. here, right, when you have exactly two fixed points, of course, then you also your transformation is conjugate to also to multiplication by alpha inverse as well, right? I mean, as I said, alpha is not, it's not the only number you have to consider. You also have to consider alpha inverse. Well, anyway, okay, consider it, and these two numbers, we are going to call them the multipliers of nu. Okay, and let me just on one last exercise, right? I mean, of course, I mean this exercise, I think it's instructive to get certain intuitive idea of, you know, how conjugation works. So you have, let's say that you have two elements that are conjugate, right? I mean, two Möbius transformations in this case. In general, it would be two elements of a group that are conjugate in the group, right? It is perfectly possible that the witnesses of the fact that they are conjugate, that is, that the elements of the group that when you conjugate when you conjugate, you obtain from one the other. It's possible that it's many of them, right? For instance, consider the identity and the identity, right? If then the whole group, any element of the group works to conjugate the identity and obtain the identity, right? Okay, so in that case, it's quite simple. Now here, I want you to see that to show that if we have these ones, this must be different from the identity. So this would be like different from. Oops. Let me move a little. This here, it's different from the identity. So different from the Mobius transformation identity. Show that the transformations that do the job of conjugate of being witnesses, that when you conjugate, that these two are conjugate, that it's a one parameter family. Okay. Some examples. So remember the notion of a loxodrome, which we define to be certain type of curve that connects 0 with infinity. Well, by applying any Mobius transformation to any such curve, we see that we can define the notion of loxodrome between any 2 points in C bar, right? And that then, given 2 points, then we have the loxodromes that connect those 2 points with respect to any alpha, a non-zero complex number not belonging to the union of the positive real numbers with the circle, right? So, in other words, we have the notion of loxodrome not only as curves that connect 0 with infinity, but actually given any 2 points, we have the notion of loxodrome. Okay, so I'm going to give to show you how some of them look like. So what I'm going to do is I'm going to take the point 0 in C bar and the point this point 50 plus 45 j in C bar. So here j is actually the complex number I, and then I'm going to draw some loxodromes. So there you can see one loxodrome. So that is this you can think of as the image of some under some Mobius transformation of some loxodrome connecting 0 with infinity, for instance. And now remember that we showed that when that given any loxodrome, the angle it forms with any circle centered at the origin was constant, right? I mean, here a loxodrome connecting 0 to infinity. That's what we showed, right? I mean, so actually what we showed was that if we consider the points 0 and infinity, and then we take the loxodromes connecting 0 at infinity with respect to a given number, to a given complex number alpha, then the angle of intersection of any of those loxodromes with any of the circles centered at the origin is always the same, is constant, right? So since the Möbius transformation that maps 0 to 0 and infinity to this point is conformal, here we should also have the same property, but now for the image under that Möbius transformation that sends 0 to this point and infinity to this point of the circles centered at 0, right? So the images of those are, as we're going to see later, the Apollonius circles of the 2 points, of this one and this one. That is this one and this one. And I'm going to show some of them. And here you can see, for instance, the statement is that the angle here, the angle formed here, is equal to the angle formed here, is equal to the angle formed here, etc. Right? And then here, well, this is not a proof, right? But you can somehow actually see it, how this angle is equal to this angle, equal to this angle, etc. Right? Okay, and now of course, if we change the alpha, then the family of loxodromes changes, and in particular, the angle they form with these other circles, the Apollonius circles, also changes. So here is when I take that angle of intersection as parameter and then see how then the corresponding loxodromes have to look like, then I have this phenomenon. Right? Okay, so these are a bunch of loxodromes connecting this point to this point. Okay, so now let's move on to examples of Möbius transformations with exactly 2 fixed points. So we have a theorem that says that any such Möbius transformation is conjugate in the Möbius group to a Möbius transformation which is given by multiplying by some alpha belonging to either the positive real numbers, the unit circle, or the rest of the complex plane, right? So let us give some example where the multipliers lie in the unit circle. So that's alpha lying in the unit circle. So our Möbius transformation is going to be conjugate to multiplying by this alpha here. So it's going to be conjugate to a rotation. So I think it should look like a rotation, right? Okay, so let's choose its 2 fixed points. So let's say this one and this one. And okay, so what I just did was to compute a matrix whose Möbius transformation has these 2 points as fixed points and has this one as multiplier. And actually, since I clicked here first, it's going to rotate according to alpha here, and here is going to rotate according to alpha inverse. Which, if you think about it, is similar to what happens with 0 and infinity and rotation by alpha, right? I mean, around 0, you do see rotation like by alpha, but around infinity, you see it like rotation by alpha inverse, right? By multiplying by alpha inverse. Okay. And now let's pick a point. Let's say that I choose the point, 0, and let's see how, let's say 25 points of its orbit under this Möbius transformation look like, right? So animated. And by this, what I mean is that, I'm going to plot 0, and then I'm going to apply the Möbius transformation and plot the result, and then up to the result apply again, and then apply again, and actually iterate, and then plot consecutively the iterations or the powers of this Möbius transformation applied to this point that I'm taking as initial. Okay. So this is like how the different iterations of the Möbius transformation look like. Okay. And let's say now that
that I just see it, you know, like all at once, and I can move, right? So what I'm doing now is kind of moving around the initial point and then seeing how the corresponding orbit under the integral powers of the Möbius transformation have to look like, right? And then it seems that indeed they are always kind of you can always plot them inside a circle, right? So it looks like here the invariant curves are circles, right? So let's draw invariant curve, yeah. So it does look like, right? This we have not proved yet, right? Because we have proved it so far only for when the fixed points are 0 and infinity. I mean, in standard examples. But then we're going to use the fact that we know that for those special for the standard examples, and we are going to use that Möbius transformations in circles to circles. So the Möbius transformation that conjugates this Möbius transformation to obtain a standard example, that conjugating one is the one responsible for this being a circle, right? Okay. So now let's give some other example where now I choose some positive real number. Let's say here, and then I'm going to click on 2 points. The first one is going to be the repulsor. The second one the attractor, right? So kind of like as if the first one were 0 and the second one were infinity for this number that has absolute value greater than 1. Okay. And then an attractor. And then I compute a matrix. And then let's take again the point 0, and then let's see how it looks like. So you see, it looks like again the orbit of 0 under this Möbius transformation, or over the integral powers of this Möbius transformation, lies on this circle, which then would be telling me that this circle would be an invariant curve for this Möbius transformation, right? And then again, this we have not proved yet. The way we are going to prove it is by saying we know it for the standard examples, and we are going to take the Möbius transformation that conjugates this one to a standard example, and that one we know has to take circles to circles. So that's the strategy we're going to take to see that this one is invariant, right? And then you see the red curves, the role they play is they play the role of the curves that are permuted by the transformation, right? So the image of a red curve is another red curve, and they also seem to be circles, right? Okay, so this is a hyperbolic Möbius transformation. Even though here it says loxodromic, here it's some error in some programming error, but the transformation you are seeing is actually hyperbolic. Okay, now let's see something loxodromic. So let's say here, and then by putting it to be with norm less than 1, what is going to happen is that the first fixed point I'm going to choose is going to be the attractor, and the second one is going to be the repulsor. So attractor and repulsor. Okay, and then compute. And then again, let's take the same point 0 and then the animated orbit. Right, so you see here. Okay, so let me draw the draggable orbit. So you see here, the orbit seems to lie precisely in something that looks like a loxodrome connecting the two fixed points. Right? And so when I move the initial point, the orbit moves, and then the invariant curve containing it that I have drawn also moves around. Notice in these kind of cases, if I zoom out, you cannot see the difference between the loxodrome and the circle. I mean, right? So that's something funny to. Well, it's funny, but it's kind of the reason is that the angle of intersection it starts forming is kind of very close to zero. So no, sorry, very close to 90 degrees. Yeah. So this is why it looks like a circle, right? Okay. So this is a loxodromic transformation. Let's draw some. You see something. Let's do this. Let me start drawing a curve and then moving around this point a little bit. So I move it a little bit. That is very close, very close, very close. Very close. Let's say that I move this one very close. Then this one very close, and so on. And then what I want you to see is that here I moved this point a little kind of close, not very much. And what happened is that of course the points in the orbit then are also kind of, you see here close to each other, and then here also close to each other, here close to each other, etc. So what you are actually visualizing is how continuity behaves for functions from the complex plane to the complex plane, right? So, okay, so I think that's what I wanted you to see.